Hello and welcome to this short session on differential thermal analysis, also called as DTE. In this online video, I'll be discussing the basic principle involved in the DTE process. Learning outcomes. After watching this video, the learner will be able to define various terms used in DTA, describe basic characteristics of a DTA curve, classify and explain different types of DTA process. So let's get started. What is DTA? DTA is a thermoanalytical technique, and like all other thermoanalytical techniques, DTA also involves heating or cooling, but most of the time heating your sample, with one difference. In addition to sample, we also use a compound called as reference. So for your DTA, take your sample, take your reference, and subject them to identical heating conditions in a furnace. Next up is the reference compound. The reference compound is an inert material, and as the name suggests, this material will not undergo any kind of physical or chemical change upon heating. Example of reference compound. The choice of reference compound depends upon the nature of your sample. So for inorganic samples, alpha alumina or even an empty aluminum pan can be used. For organic samples like polymers, silicon oil or octyl phthalate is used as a reference. Next is a sample. Sample or analyte is a heat-sensitive compound, and so on heating, your sample will undergo either an endothermic reaction or an exothermic reaction, causing a physical or chemical change in the sample. These terms, endothermic, exothermic, are very important to understand the DTA process, so we'll see them in the next slide. So here's my sample, which I've been heating for quite some time now, and at some point, my sample is going to undergo either an exothermic reaction or an endothermic reaction. So what is an exothermic reaction? Whenever your sample undergoes an exothermic reaction, then the energy contained in the sample is converted into heat energy, because of which the sample temperature increases. So in all exothermic reaction, the sample temperature will increase. And the exact opposite would be true for an endothermic reaction. So in an endothermic reaction, the heat energy from the surrounding is absorbed by the sample, and this absorbed heat is converted into some other form of energy. The main point here is that the absorbed heat is not used to raise the sample temperature. Instead, it is used for some other process like melting or evaporation of the sample. So in all endothermic reaction, the sample temperature actually decreases. So what's your main takeaway from this slide? Exothermic reactions will cause the sample temperature to increase, whereas the endothermic reaction will cause the sample temperature to fall. The next term is measured parameter. In DTA, the measured parameter is a value called as delta T, which is the temperature difference between the sample and the reference. So this value delta T can be obtained using the formula Ts minus Tr, where Ts is the sample temperature and Tr is the reference temperature. Please note that delta T is always calculated as Ts minus Tr and not the other way around. And here's the reflection activity, and this is my question. The measured parameter delta T can be a positive value, a negative value, or even 0. Pause the video and record your answer with suitable reasoning. Once you're done, you can play the video again. So I hope all of you have recorded your answer, and here's my answer. Yes, delta T can assume any three of the values, positive, negative, or 0. If you remember, delta T is calculated as Ts minus Tr, so for all the conditions where the sample temperature is exactly same as the reference temperature, delta T would be 0. Other conditions like your exothermic reaction, where sample temperature is greater than the reference temperature, the delta T value is going to be a positive value. And all the conditions wherein the sample temperature falls below the reference temperature, the delta T is going to be a negative value. Now, what is the significance of this delta T? This differential temperature delta T is plotted against time or temperature. Now most of the time delta T is plotted against the temperature, and this plot of delta T versus temperature results in a curve called as DTA curve. This DTA curve is very important to obtain information about the sample that you are studying. So in the next slide, we'll see the DTA curve in detail. So this is what a DTA curve looks like, and like all other curves, the DTA curve also has two axes, the y-axis and the x-axis. On the x-axis, we plot the temperature values. So for this particular experiment, your sample was heated from say a temperature of 200 degree to 1500 degrees. So the temperature values are plotted on the x-axis and the delta T values go up on the y-axis. So if you see at this point, the delta T value is 0. And above this point, delta T will be positive, whereas below this point, delta T is going to be a negative value. Okay. Now if you look carefully, the DTA curve actually consists of three different parts. Okay. The first part is very easy to identify. This is the flat portion, also called as the baseline of the DTA curve. The second part is a downward peak, also called as an endotherm. And the last part is an upward pointing peak, also called as an exotherm. So in the coming slides, we'll see that why is it that the baseline is a flat line, the exotherm points upward, whereas an endotherm points downwards. So in order to understand all this, we need to look up the DTA process in detail. So as mentioned before, in DTA, we subject the sample and the reference to identical heating treatment, which means we stick the sample and the reference in the same furnace and increase the temperature at a predetermined rate. Next, we measure the sample and reference temperature using thermocouples. This will give us a value of TS and TR. So right now, say I've heated my furnace up to 500 degrees. So at this point, the sample temperature TS is 500 degree and the reference temperature TR is also 500 degree. So right now my TS is equal to TR, which means the delta T, which is the difference between the two, is 500 minus 500 and this value is 0. A 0 delta T value will give you the baseline of a DTA curve. So let's see the DTA curve now. Notice the x-axis of the DTA curve and notice that up till 500 degree, the DTA curve is a flat line. This means that up to 500 degree, my sample is pretty stable and is not undergoing any kind of reaction, neither endothermic nor exothermic. Okay, so throughout this range, the sample temperature is exactly same as the reference temperature. And so the delta T value is 0. You can also see the dips and the upward peak, which will be discussed in the coming slides. So I hope it's clear from this slide that so long the sample temperature is same as the reference temperature, the delta T value will be 0 and the 0 delta T value gives you the baseline of the DTA curve. Now in the next slide, we'll discuss the formation of an endotherm. Okay. So let's discuss the formation of endotherm, the downward peak or the negative peak in the DTA. So I continue heating my sample and the reference and say the furnace temperature hits 600 degree and ideally the sample temperature and the reference temperature should also be 600 degree. But at 600 degree, my sample undergoes an endothermic reaction. Now remember from our previous discussion, an endothermic reaction will cause a decrease in the sample temperature. So although the furnace temperature is 600 degree, the sample temperature is 500 degrees, which is 100 degrees lower than the set temperature. But what about the reference? The reference, being an inert material, will not undergo any kind of reaction, neither endothermic nor exothermic. And so the reference temperature TR will be still 600 degree. So let's get all our temperatures straight. The furnace temperature is 600 degree. The reference temperature is also 600 degree, whereas the sample temperature due to an endothermic process is less than 600 degree and is somewhere around 500 degree. So let's go ahead and calculate our delta T, which is Ts minus Tr, which is 500 minus 600, and this difference is minus 100, which is a negative value. So whenever we plot a negative value, the resulting curve is going to be a downward peak. So plot of delta T, a negative delta T versus temperature will result in a downward peak in dTA. So I hope it's clear from this slide that for an endothermic process, the delta T value will be negative value, and whenever we plot a negative value against temperature, the resulting curve will be a downward peak, also called as an endotherm. So now we know that in a dTA curve, the downward pointing peak is called as an endotherm, whereas an upward pointing peak is called as an exotherm. So the formation of an exotherm is an exercise. Describe the formation of an exotherm in the dTA curve. And that's all for today. Thank you very much for watching.